Hey, this is Pat Martin, and this is another Dex tutorial. And in this tutorial, I'm going to quickly cover is the machine learning capabilities that now newly exist within Dex. And I'd like to, first and foremost, actually thank Haifeng Li. I hope I said the name correctly, for his work on a package called Smile. So what's great about this is it has open source licensing, and it implements most any machine learning algorithm of significance out there. Not really sure about all, but there's a few gaps here and there, K modes and stuff like that. But he's really done a wonderful job, and it's available on a JVM. You can use it with Scala. You can use it with Java. I would assume Clojure or any of the JVM languages could be leveraged with this. And performance looks good. Results have been great. And he's really done a great job also documenting from a user guide perspective some of the high points of machine learning. Why do you do this? Why do you do that? And there's pretty good Java docs as well. It's pretty helpful, and the interfaces are very consistent. So once you learn how to call one of them, you pretty much know how to call most of them. Though there's a few that have a different arguments. Really, they're mostly looking for data in the form of an arrays of doubles. And anyway, enough on that. I'm going to skip into Dex, and I'm going to open this up. And the first thing I'm going to do is point out that there's a new section here, and it shows machine learning. And if you click on any of the components, ARM, you should see documentation, and you should see the live user manual. Sometimes you won't get this if your proxy blocks the content, because it actually does a web hit to get out to that. FP growth, which is the frequent pattern growth algorithm. We're going to cover decision trees. Here's the documentation on that. The prediction component, and then lasso regression, linear regression, ridge regression, k-finder, k-means, and x-means. So I'm not going to do these exactly in order, so I'm going to go ahead and open up a project. I'm going to go into the machine learning section that should be available with the Dex distribution here, and I'm going to jump directly into training a decision tree. So each one of these starts off with some online documentation, and the first thing we're going to do here is we're going to read the iris data set. And then we just executed this whole flow, but I'm going to go through the results of each one of these tasks one by one. So data looks like this. We have sepal and petal measurements, and we have a species correlation. So things we could do with this data set, maybe predict this, that, or the other, predict the species or the sepal length. And this is just an alternate view into the data. Only difference is it shows us all the data, whereas this is only going to show the first 100 rows of data. This is showing all the data. And then over here is the decision tree. So I'm going to run through. So this is going to be fairly consistent setup across the machine learning tools. But in the case where we persist a model, whether it's a regression model or a D-tree model, or maybe k-means, clustering, etc., we're gonna persist it into an MDL file. And typically we're going to have the type right there. So D-tree is of type D-tree MDL. And then we have the ability to autosave on run or to save the model manually. So the reason there's an autosave flag is sometimes we run this type of stuff in an automated setting, and maybe it's auto-learning based off of data it sees real-time in a production environment. So in that case, we want to be able to auto-save without having a human click the Save Model button. Then over here we got the split rule, and we have Gini, entropy. I don't think that's actually a split rule. I think that's a problem. And then there's max nodes. which is going to define the complexity of the model. So we start off with 4, we're predicting species, and we're storing the column in something called trained prediction. So what if we were to bump the max nodes up to 100? And over here we got the percentage of the performance information. So we predicted 97.3% correctly, so 146 out of 150, with only 4 decision nodes that look pretty simple laid out over there. But if we were to run it with the 100 max nodes, let's take a look at what that would look like. So we only have 4 variables, so you can only have 4 things of various importance. Looks like the most important was petal width, followed by sepal length, closely followed by petal length, it looks like. So the model looks drastically different. It's much, much more complex, and it classifies everything. Kind of cool. Though you have to wonder, whether those edge cases are being overfit or not. Probably are. Simpler is better. So let's go to another extreme here. Let's take a look at, what if we only had 2 nodes here? Let's look at what happens in that case. So with only 2 nodes, the most important thing is petal length, and if the petal length is less than 2.45, it's setosa. Otherwise, it's versicolor. So we didn't even have room in a 2-node model to even classify the third iris class, which is virginica. So obviously, we're not getting good results from a 2 max node, but it is kind of useful as a human being to look at the model and say, wow, okay, I understand the split there. What if I wanted to see? What if I didn't want to see petal length? Maybe I want to see a 2-node model. I'm going to throw that out. I'm going to re-execute it, and then we'll look at it in terms throwing petal length out, and we see, okay, well, petal width does a pretty good job as well. So if the width is less than 0.8, it's setosa. Otherwise, versicolor. Maybe a 3-node model makes more sense, but the point here is we can take a look at variables in isolation using this. We can up the nodes here, look at only sepal length, and we can see, okay, now we have room to classify all 3 flower species with 3 nodes. And if I only had sepal length, I could do a 65% prediction. And I would do it like this. If sepal length is less than this, and if it's less than that, it's setosa. Otherwise, it's versicolor. So, basically, sepal length increases across setosa, versa length, and virginica. I've had all the variables, and I wanted a fairly simple model. Re-execute it, take a look, and it looks like it only takes a look at the sepal length and petal width, or petal length and width here. And it's able to classify it 96% of the time. Okay, so that's that. Next thing we do is we're creating a feature here. We're creating 2 features actually: the prediction number and the status. So this is really just for the Dex visualization, and then we're selecting the status, the prediction number, and then the train prediction. So what we're going to get here, since we're feeding into a scatter plot, is that's going to be the legend. So that's going to be the colors. This is going to be on the x-axis. That'll be on the y-axis. The rest of these will be in the tooltip. And what it's going to show us is it's going to color the things that are incorrect versus correct. And I can see, where those mistakes were. If I wanted to, I could turn this off, and I could focus only on areas where the prediction was incorrect. So I can see it was incorrect because we predicted versicolor. However, it should have been virginica. So that's a useful way to maybe take a look at a population and isolate on cases where your model is failing on the training case. So next thing I'm going to do, since we saved that model off to an MDL file, is we're going to run the prediction. So all it's going to do is going to read in a data set that has the iris data, but it lacks the species data. So to prove that, I'm going to show this, and we see that we have everything except for species. Then over here we load the IRSD tree model. We're going to put it in a destination called prediction. And here we made 150 predictions. We can see that the features are all doubles, and these are what the features are. And then lastly, we're going to visualize it in parallel coordinates, just to show some alternate visualizations of, where you can really marry up some of the strengths of Dex versus, versus the capabilities of the machine learning. If you can start communicating what the machine learns effectively, that's a really powerful tool. So that's decision tree. It's really good for exploratory analysis. It does pretty good analysis on its own, and it's really nice because it's transparent to the human. It imparts machine knowledge to the human, which is pretty rare. Okay, so next thing I just loaded is ARM. It stands for Association Rule Mining. And what we're going to do with ARM is we're going to read in a presidential data set. I'm going to go ahead and execute this. So just ran everything. And the data set looks like this. I've used this quite a bit in previous demos. But presidency, president, party, home state. So the number of office they took. So George Washington was the first president, then John Adams and Thomas Jefferson. The parties, and they've evolved in names over time, and the home states they're from. So what we're going to do here is we're going to look at party and home state, and we're going to look for assertions that we're 70% confident about that occur across at least 2% of the population of the data set. And then we're just going to do some fancy selection and look at antecedents and consequence and map it to support. And we're going to visualize it in a Sankey diagram. So since we have this laid out, and I'm going to show both of these at the same time so we can see the net effects of decisions I make over here. And I did that just by control selecting multiple columns. So what I see here over to the right is that people with the presidents that had a home state of Ohio, there's a large number of support for them being Republicans. If they're from Texas, looks like there's a large number that are Republicans. Indiana, Iowa also follow. So what if I were to say, okay, I want to see relations that have a 4% data set frequency. I'm going to go ahead and re-execute that. This is going to update itself. And I see that the number of categories were really diminished. So the only things that have that level of support are that you're a Republican from Ohio or Texas, or that you're a Democratic Republican from Virginia. And maybe easier to see if I open that up a little bit. If I were to say I want to be 94% confident, let's see what I could assert there. Then we lose our Ohio Republican assertion, and we just end up with the Democrat Republican from Virginia assertion. Or association is a better way to say it. So that's it. It's really showing the best of Dex and the best of machine learning, which is to be able to display visually what you've learned. I'm going to move to the next one, which is frequent pattern growth analysis. And what we have here is we're looking for frequent combinations of party and home state. We're looking for support of 13, and I'm going to also visualize a bar chart as we go over here to the right, so we don't have any data yet. But I'm going to go ahead and execute based on what we want to see there. And what this is showing me is that, okay, well, there's about 15 Republicans. Let's see, support of 10 for Democrats, so 10 Democrats. Home state New York is another common one, Ohio. And also it found that same relationship we found in association mining, which is Republicans from Ohio. So it found a tuple of 2, an association of 2 with the FP growth. So that kind of shows on larger data sets, it may be interesting to be able to do things like, if customer A bought product B, then they probably also bought product C. So that's kind of the area where you would maybe start using FP growth. So I'm going to move on to, let's see, association, covered, classification. So I'm gonna move on into clustering. So again, we have our documentation. We also have a new data set. It's the Titanic data set, and that was downloaded from Kaggle. And let me see. Let me take a look at. Didn't mean to show that. Meant to show this. So you can get these data sets over on Kaggle. It's a great contest, especially if you want to whet your data science skills. This data set has a lot of interesting wrinkles to it. Very easy to get some pretty good predictions out of the initial data set, so they give you hope to start off with. Then if you want models to perform better and better, you got to do a lot of data cleanup, a lot of intelligent feature extraction. You got to really wrap your mind around a data set. And what's really nice about this is it gives you an overall feeling for what data science really is, which is why there's so many participants in it. It's just a really good tutorial on data mining, data science, whatever you want to call it. So, having said that, let's go ahead and execute this. Let's take a quick look at the data. And over here, let's see, read in all the data. Let's see, expected to see, oh well. Okay, so we got a number of fields here: passenger ID, survived. You can get more information on the data set from the Kaggle site. But the first thing we're going to take a look at here is K-Finder. So I'm going to go ahead and I'm going to set this up to look at all K from 2 to 100. And the reason what K represents here is the number of clusters. So what we're doing here is we're taking a look at the age field, and we're trying to figure out what is the optimal clustering for age. So, if you look at this, it looks like this is called the elbow plot, and we're graphing distortion, what Hyping calls distortion in his k-means model, and we're graphing that versus the value of k. So it really looks to me like at around 6, around 6 is where we hit diminishing returns. We get a jump in distortion from 18,000 down to 8.4 thousand, and then we kind of hit diminishing returns, arguably. If we wanted to look at it a little more closely, maybe limit the k-means to 10, and then execute that, and then we can kind of see it zoomed in a little bit. And it looks like diminishing returns to me, maybe at even 5. I'm going to set it to 5. So I'm going to jump to the next one here, and currently it's got clusters set to 7. But I'm going to reduce this to 5, and I'm predicting age here. I should be calling it age cluster. So what we're doing is we're going to cluster. We're only going to consider the age category here, the age column or feature, whatever you want to call it. We're going to output the cluster into age. And we're going to use that key mean we decided on in a key finder with a value of 5, and then we'll execute this with that cluster size, and our graph's going to update here with 5 different clusters, and we can see the outlay of age here. So I can see that looks like cluster 4 is older people, then cluster 0, and then over here cluster 2. So we can see that it did take these values and do, I don't know, some sort of k-mean centroid based clustering. And over here to the right, we can see the distortion. We can see the model serialized out to a string. We can see that it's a pretty well, except for that last that last k-means has different performance than the rest. We can see the centroid point. So, you could play around with this if you think that more clusters make sense. Jump to 18, and don't know if that'll make sense, but we can take a look at those types of things that it may have discovered here. So it looks like it just did the age and just kind of tightened up the binning. But I'm going to jump back to 6. This is kind of how to read that kind of stuff. And keep in mind that's only I think the first 100 entries. I'm not sure if there's a sanity check on that or not. If it's not, it will be when I get back to coding it. But okay, so we're using our cluster as 6. I'm going to go ahead and save the model. I hit Control S. You can't see it, but when you look at the data, what's coming out of here is we've got this age cluster over here, and I need to change this name. So I need to go ahead. I'm going to go ahead and clear this out. I'm going to run this, and since I cleared it out, I'm going to get an exception telling me I need to initialize the D tree. But since I renamed that column, I need to tell it about that column. So age cluster, I'm going to throw that in over there, and I'm gonna say, okay, let me start off with maybe 10. I'll just say 9. That's where it ended up, and we're going to classify the survival rate based off of the age cluster. So we're going to take a look at how those clusters worked out, and I'm going to reduce this to 6 to match our number of clusters. And let's go ahead and take a look at the ones that the clusters that D-Tree thinks is actually of value. And this is kind of interesting. So when we have 6 nodes, we're not able to get to anybody who survived. Everybody died. So we need to up this. We don't have any decisions coming out of this that make sense. So I'm going to up it to 9. And I still don't. This is kind of suggesting that age alone is not the greatest predictor for survival. However, I'm going to keep up in the nodes, and let's see what's going on here. All right, I'm going to keep upping it until I get something that makes sense here. Yeah, I may have to. I'm gonna play around with this a little bit more too, and let me make sure. All right, so that's outputting the age cluster, and I'm gonna go ahead and run it again, and let's see what comes out of this with 8. Okay, well, okay, I'm getting a decision there with using 8 clusters. So what I just saw is probably there wasn't a strong enough relationship with only that number of clusters and that number of max nodes to do a prediction on survival. So I had to play around with that a little bit, and maybe it could indicate that I need to keep playing around with that age cluster. But certainly when I up the bins, now I can see a lot more behavior being driven off of that. But anyway, that's more time that I really could afford to spend on that then. But that's it for the k-means. So I'm going to gloss over x-means pretty quickly. The only difference between there's more differences, but the primary difference interface-wise between x-means and k-means is x-means you only have to know the maximum number of clusters you're willing to accept. So you don't have to make a decision about k up front. So this will be interesting in a different respect. So over here we're predicting P-arch and sib-SP. That stands for parent, child, and sibling spouse. So what this is a counter. How many parent/children accompany you on board the Titanic versus sibling and spouse? And the idea is that if you had a lot of family relations, it would have some predictive behavior on whether you survived or not, and those types of relations. Women and children first, stuff like that, going down with the ship, I guess, is the idea. So we're calling this relation cluster, And then I'm adding a row number, selecting columns, and then I'm visualizing it in multiples. So I'm gonna start off just by executing this, and then we'll look at the multiples afterward. Let that run, and x means looks like the x means ended up with 9 clusters. So looks like you really got to go to at least 9 clusters to get the behavior out of these 2 interactions here, these 2 things we're analyzing. So since we're analyzing 2 things, we also have value 1, value 2. We're looking at the clustering of value 1. If I wanted to look at value 2, I just shift that upward. And then we can see a whole different outlay of values. So that would be the sibling spouse clustering that we see there. That's just different ways to look at it. And along the top, we're looking at the various clusters here that we can squelch them just by turning them off, either over here, or if I wanted to do a quick filter, look at clusters 0 through 2, I could do that. Or any sort of filtering you would want to do here is available. And then again, we got our model performance. And all we're doing over here is we're looking at the performance in a different visual. So X means appended its clustering information onto the stream. Over here we added row number. Over here we selected the columns we wanted to look at. So we're going to subdivide everything out by relation cluster. We're going to series things out or legend them out by whether they survived or not. And then we're going to look at the row number versus the parent arch relationship here. And this is a little bit of a bug in the WebKit from JavaFX. I can't fix it, or I would. But essentially, the lines don't match up. When you save this stuff off, it saves and views appropriately in Chrome. But the WebKit isn't 100% HTML compliant. Each arch pushes the edge, and that's the visual we're using here. So this is kind of interesting. And we can see we really need to see the legend, so I'm going to turn that on over here. And we can see that 0 for died, 1 for red, for survived, or blue in this case. If we wanted to, we could say, okay, well, I only want to see people that survived. So that's going to show me, and it just switched the color up because there's only one series. So I can see the survival rate there. Or if I want to see only the people that died, just to get an idea of which clusters contain more, I can definitely see that this is not a surviving cluster. The people that ended up in this one probably died. And if I wanted to be able to see all that side by side, just turn that filter off. And another thing I could have done is I could have gone into the cell dimensions and then increase the width to something that draws this out a little bit more. I can collapse this over here so it's not taking up so much room. And I can just basically get an idea for the density of survivors to non-survivors. So that's the X means, and sake of time, I'm going to move on here into the next section, which is very important, which is regression. And I'm going to start off with the simplest of regressions, which is a linear regression. And what we're going to look at is some garbage collection data, and I'm going to go ahead and throw just to get an idea of how much data is piping through here. Not that it's impressive, it's not, but just to give us a feel for it. So it looks like we got about 1,800 rows of 29,000, totaling 29,000 items spread across 16 columns. So over here we're selecting a subset of that, and then I just move this down here, and we'll take a look at what makes it past that column selection. And we're just looking at a subset of about 10,000 items of data here. And what I'm doing here, and I didn't have to do the filtering. It just made it easier to deal with downstream. I didn't care about the other fields. So what we're doing here is we've decided we're going to do a linear regression on all these selected columns, and it's going to add a column for each one of these that contains the regression behavior. And keep in mind, I'm only seeing the first 100 rows across here. So even though this looks like a horizontal line, when you look at the overall data set, it's probably going to have some slope to it. You're only seeing the first 100. It's kind of a sanity check, because if we had 1,000,000 items, I don't think I would like the performance of this thing graphing out versus 1,000,000. So later on, I can graph it out if I want, but I have to do it myself. So so what we're doing is we're basically adding regression lines, and when I look over here, I'm gonna graph it out into a line chart. And what's going to happen here is I've got a co-browser that whenever I run this, it's gonna update itself. So I'm going to try to show both of these windows at the same time, and I'm going to maybe surf off to another page here, and then I'm going to hit execute, and it's going to auto drive this session over here with the output from our analysis here. So really kind of interesting. The reason I laid it out here the way I have is so we can basically take a look at things side by side. We can look at this field versus that and take a look at that behavior. Kind of interesting. We can see why that regression line looks about right. We can see this thing was all over the place over this time, and looks like a pretty good estimation. So that's it for linear regression. Now let's get into some of the more advanced forms of regression here. And while I do that, let me just say again, thank you to Haifeng Li. Awesome stuff he has. And ridge regression is no slouch either. It does pretty well. So okay, got the iris data set. We've already looked at that, and so we're already familiar with it. And what we're doing is we're going to store our model in this iris ridge model, and we're looking at sepal width, petal length, and blah blah blah, and species. And we're trying to classify it this time. We're trying to predict the sepal length. So let's pretend that for some reason our scientists can't take sepal length. We need to infer it based off the other measurements, or maybe we're just trying to fill in some missing data because there were some sloppy data entries. Who knows? Maybe you're doing imputation, data imputation. There could be a lot of reasons, but I'm going to go ahead and execute. And this time we're getting a window broken into 3 segments. Over here we have our our visual controls. We're not going to play around with that too much, so I'm going to shrink it down. And we can see our actual versus predicted, and looks like the performance was pretty good over the first 100 rows or so. Looks pretty good. Then we got a little bit of what Dex does, which is selecting, and we're looking at and preparing stuff for other visualizations. And in this case, we're just doing a visualization across the whole data set of our ridge prediction versus the sepal length. Looks pretty good. So that's about it for that. And again, if we wanted to, we serialize that prediction out, so we can simply run a prediction based on the model, and look at the same thing side by side here on a data set that lacks that entry altogether. So here we're doing that same prediction on a data set that lacks it. So that's where the utility is. Last but not least, and I'm not going to go too deep into it other than showing it, it basically works exactly the same way as ridge regression, only different. Algorithm slightly different, but I find the results are pretty much neck and neck, and I'm sure there's some edge cases where one makes a difference versus another, but I've yet to find it myself. And kind of cool here. we can do some experimentation real quick. Maybe say we only have petal length and petal width, and what if we're trying to predict the sepal width instead? Then let's go ahead and execute, take a look at what that model would look like. Looks like we don't do a super good job based off of that. Looks like we need the other data. So what if we give it sepal length? Go ahead and throw that in there. At least on the first 100. So I don't know what's happening after that. But this is the types of experiments that you would maybe run through Dex here. And it looks like I was auto saving. I should have probably maybe had that turned off, but that's okay. Anyway, I think that's about it for Dex and machine learning, and I guess going forward, I'm looking to put some new algorithms out there, and based off of Smile, because again, that's a wonderful project, and I'm getting a lot out of it. And that's a wrap for now. So thanks a lot for listening. Bye.